Hello, this is Jennifer Martinez, and in this video we're going to look at applications of linear systems. The first application that we're going to look at is known as Leontief model, or sometimes called the input-output or production model. I'm going to start with a little history of Leontief that's given in the introduction of this chapter. So let's go ahead and read this. It was late summer in 1949 when Harvard professor Wassily Leontief was carefully feeding the last of his punch cards into the university's Mark II computer. The cards contained information about the U.S. economy and represented the summary of more than 250 pieces of information produced by the U.S. Bureau of Labor Statistics after 2 years of extensive work. Leontief had divided the U.S. into 500 sectors, such as coal, automotive, and communications, and so on. For each sector, he wrote a linear combination that described how the sector distributed its output to other sectors of the economy. Because the Mark II was one of the largest computers of its day, it could not handle the resulting system of 500 equations and 500 unknowns, so he had to distill the problem into a system of 42 equations and 42 unknowns. So if you read the second paragraph here, it took the Mark II 56 hours before it finally completed the solution. Leontief, who was awarded the 1973 Nobel Prize in Economic Science, opened the door to a new era of mathematical modeling in economics. His efforts at Harvard in 1949 marked one of the first significant uses of computers to analyze what was then a large-scale mathematical model. And since that time, researchers in many other fields have employed computers to analyze mathematical models. Because of the massive amount of data involved, the models are usually linear. That is, they are described by a system of linear equations. The importance of linear algebra for application has risen in direct proportion to the increase in computing power, with each new generation of hardware and software triggering a demand for even greater capabilities. I like this application because not only does it show the importance of linear algebra for its applications and how linked computer science is with linear algebra, it gives an example of what we're going to be doing in this section, which is described by a system of linear equations. So let's go ahead and look at our first example. Our first example is going to be a homogeneous system in economics. And we are going to look at a simpler model than the 500 equations and 500 unknowns that we saw in the introduction. The model that we're going to look at here is called the exchange model, and it's also by Leontief. So suppose a nation's economic is divided into many sectors, just as the one that we saw in the introduction, such as manufacturing, communication, entertainment, and service industries. Suppose that each sector we know its total output for 1 year, and we also know exactly how this output is divided or exchanged, it's called the exchange model, among the other sectors of the economy. Let the total dollar value of a sector's output be called the price of that output. Leontief proved the following result. There exist equilibrium prices that can be assigned to the total outputs of the various sectors in such a way that the income of each sector exactly balances its expenses. So let's look at the following simple example of just 3 economies. Suppose an economy exists of coal, electric, and steel sectors, and the output of each sector is distributed among the various sectors as known in Table 1. And here is Table 1 down here, where the entries in a column represents the fraction parts of the sector's total output. We're going to denote the prices in dollar value of the total annual outputs of coal, electric and steel sectors by PC, PE, and PS respectively. If possible, find equilibrium prices that make each sector's income match its expenditures. So here's our three sectors. Here's our table of distribution of outputs. So let's just look at one column here. Each column represents the total output of the sector. So this middle column here is the electric sector, and it's divided into three categories. 40% is going to go to coal from electric, it's the outputs. 10%, or let's do 50% is going to go to steel, and then the remaining 10% is going to stay with electric. So let me go ahead and show that here. So the electric sector is going to have three outputs. 40% is going to go to coal, or 0.4. 50% is going to go to steel. And so the remaining 10% is going to stay. The first column is the outputs for coal. So 60% is going to go to electric, 40% is going to steel, and they're not keeping anything. Again, coal, the outputs of coal are 60% going to electric right here. So that would be 60% right here. And 40% going to steel. So 40% to steel. And remaining 0% to itself. The last column, steel. 60% to coal. 20% to electric. And 20%, remaining 20% is going to stay within steel. Steel. So when you look at the columns, down each columns, it's where the outputs go. So if we look across the row, we're going to see what we need as inputs. Our first row here tells us that coal receives 40% of its electric output and pays for, by the way, and 60% of the steel output. So if I let PC be the price of the total annual output of the coal sector, which was given here, PC denotes the price of the total annual outputs for coal, electric, and steel, and PE be the price of the total annual output for the electric sector, and PS be the price of the total annual output of steel, of the steel sector. So again, our first line told us that coal spent 40% of the total price, the price of the total output for the electric sector, which was the PE, plus 60% of the PS, which is the total annual output of the steel sector. So we have an equation. The price of coal is 40%, the price of the electric plus 60%, the price of steel. Then we could do the same thing here, that the the cost of electric, or electric spends 60% of the price of coal, 10% of to itself, the price of electric, and 20% to the steel sector. So we get PE equals 0.6 PC plus 0.10 PE plus 0.20 PS. And finally, the last row, doing the same thing, that's steel, so PS would equal 0.4 PC plus 0.5 PE plus 0.2 PS. And this is the system we're going to solve. So let's bring everything to one side. If you notice, everything has a variable, so it's going to be a homogeneous system. The first equation, I'm just going to subtract these two. The second one, I'm going to do the same thing, subtract the PC. When I subtract the PE, those are like terms, so this would be negative 0.9 PE. Or actually, that would be plus 0.9, sorry. and then that would be negative 0.2 PS. And the last equation would be bringing this one over, negative 4 PC, negative 5 PE, and then subtract negative 0.2 to the 1, and you get plus 0.8 PS equals 0. Now I'm going to look at this augmented matrix and solve this matrix. I'm just going to go ahead and use my calculator to get the reduced row echelon form of this matrix, since we have a lot of decimals here. So I'm first going to go to second matrix, and then I'm going to go to edit. I'm just going to go ahead and change A because I don't care about it, but if you want to keep A, you can do it in B. So I'm just going to leave A highlighted here, and I'm going to go to edit and hit return, and we have a 3 by 4. So I'm going to make this a 3 by 4, and then I'm just going to type in this matrix. 1, negative 0.4, negative 0.60, negative 0.6, negative 0.20, negative 0.4, negative 0.5, 0.8, and 0. And then what I'm going to do is I'm going to go to second quit to get out of this. And then I'm going to go back to matrix. And now I want to do math on this matrix. So I'm going to go to A. What I'm going to choose, if I go up, I can find here, this one is row reduced echelon form. This one, if you just want row echelon form, you would choose this one. And we want it of matrix. So I go back to the matrix, and right in there it would put A. I just pressed 1 for A because 1 was A, and then close the parentheses, but you really don't need to. And there we have it. Let's move that over. There that is. Let me go ahead and close this. If I round to 2 decimal places, maybe I would get 1, 0, negative 0.94, 0, 1, negative 0.85, 0, and then a row of zeros. What does this mean? Well, if you remember from this first column, this was PC, this one was PE, and this one was PS. So that tells us that P minus 0.94 PS equals 0, or PC equals 0.94 PS. And the second one tells me that PE minus 0.85 PS equals 0, or PE equals 0.85 PS, and we know that PS is free. That's our general solution. And if we write this in parametric form, let's call PC, should do it in order, PC, PE, PS, it's going to be 0.94 PS, 0.85 PS, and PS is free, so I'll just leave it. Oops, that's S. So if I factor out a PS, I get the vector 0.94, 0.85, and 1. P is called the equilibrium vector because the equilibrium price would be this vector. This would give the expenditures for each sector, for each choice of PS, that is. For example, if PS is 100, or if the total annual output of the steel sector is $100, then PC would be 94 and PE would be 85. Let's look at a practice problem just to practice making the table. Suppose an economy has 3 sectors again: agriculture, mining, and manufacturing. Here the 3 are. Agriculture sells 5% to mining and 30% to manufacturing, and retains the rest, so that's 35%, so 65% would add up to 100 there. Mining sells 20% to agriculture, 70% to manufacturing, so to add up to 100, it retains 10%. Manufacturing sells 20% to agriculture, 30% to mining, so it retains 50%. So the table would be the outputs of each. So the first one, agriculture, would be 65% to itself, 5% to mining, and 30% to manufacturing. Mining is in the light blue, 0.2, 0.10, and 0.70, and manufacturing is in the light green, Notice how all the columns must sum up to 1.